think that so maybe we start. So welcome to another seminar of our ARA program, and today we'll have Marcel, unfortunately his last day, so if you have any questions extra from today that have to be, we'll schedule a discussion and we'll have it over Zoom, but we're very happy to have Marcel Vonk talking about Painlevé and exact WKB.
Yep, thank you. And indeed, I'll be part of the program for the rest of the duration. Online. So thanks for allowing me. Also, thanks for the 4 weeks that I've been here. Very nice. What I want to talk to you about today is see here, Painlevé I and exact WKB, which are things that many of you know a lot about. You get scared to tell you things about topics that you may know more about than I do. But we'll see. And what I want to do is review these topics a bit, because we did them and then discuss recent work that I did with my PhD students, Alexander van Spaendonck, here, was also a workshop. A paper that was put on the archive a few months ago. Before talking about that recent work, though, I want to talk a little bit about how all of this came about. The story of this project really starts years ago. Actually, Ricardo and I studied resurgence in string theory and models like the matrix model and the equation. I'm not going to put pictures of everyone I mentioned on here, but when I started making this talk, maybe it's not talk, it's a template. There were pictures are from the so what we did there was describe transseries solutions to these equations, in particular that which are resonant to transseries. And back then we didn't know as much as we know today. So what we did was we computed the number of Stokes constants numerically. Here you see the table. It's also a paper from 2007. And back then only the first one was known. So this is the famous Stokes constant. One parameter. That's an exact expression in terms of square root pi, 43, and so on. That one. Shortly before our paper, actually another one had been included numerically. I think that's the third line from below. But the other ones were new at that time. Should I stand closer to
Is it breaking or is it very low? Can you hear us? No.
Continue until the directions.
I can listen. But the microphone is quite. Let me just check.
Two microphones, maybe my microphone. No.
Change microphone. And try it like that. Last time it worked. Maybe that works again. We'll figure out.
No, I'm not allowed to speak.
Oh, it's. Is now better?
Yes.
Yes.
Thank you. Okay, so we had all these rather mysterious at the time numbers, and back then we asked ourselves, well, is there a way to compare exact values? Are there any relations between them? And of course, they tell you something about Stokes homology, and if you somehow sum into an exact expression for Stokes homology. So that was 11 years ago. In the meantime, many of these questions have been answered. So this started with work by Ricardo and Ines in 2013 already, where they discovered a lot of the relations between these constants. And how we can package these numbers and how we can package these numbers is also explained very clearly in the primer that they wrote later in the project together. And then this year actually a paper appeared where Ricardo and three of the students, one of them in the audience, really computed these numbers and gave their analytical values in closed form. So that's you might now say, well, all of the questions are basically answered, but there's still enough to be learned. And the story sort of has a midpoint because in 2017 I actually applied for the PhD student, applied for money for the PhD student that someone would become Indian. And then this last question was not answered yet. So in that proposal I still mentioned the Stokes constant as a problem to calculate. Now, as this goes with applications, you don't get money immediately, so I have to reapply and reapply and reapply, and then 2020 eventually, Alexander started. At that point, we already knew that the numbers had been computed because the students had been given talks about it and so on. But still, this question was lingering around, and it turned out that there was still a lot of value in studying it again and study it from maybe a slightly different point of view. Using techniques by Takei and Iwaki, that's a lot about this as well, in the direction of isomonodromic deformation. And this method was also discussed in the paper by before Ricardo and Baldino on the Schwick paper. So that's what we set out to do, and what I want to tell you today is sort of the extra results that you get when you really study this approach and work it out in more detail. There's a lot to learn. So what I want to tell you about is first set the stage, talk about the Painlevé I equation, and like I said, many of you are very, very familiar with the equation, but still I want to set some background. So I'll tell you about it from 2 points of view. First of all, from the transseries point of view, the 2-parameter transseries, and how it's going to appear there. And then from the isomonodromic deformation point of view. And then I'll tell you what the results of our study are. So these pertain to symmetry and non-uniqueness transseries parameters. How you can encode special solutions like concave and deconcave solutions in these parameters. Of course, I have to show you that we can reproduce these exact numbers for the Stokes constant. And then I want to end by telling you a little bit about numerics. How can you check these things numerically? First of all, because we numerically check our results, so I can show you that all the stuff I tell you before actually works when you go to numerically and check it. But also that because I want to tell you a little about the techniques that we use. And I think this whole program, one of the aims, of course, is to share tips and tricks with one another. I think Gerald's talk last week, for example, was a very nice example of that. So maybe I can give back a little bit and tell you about tips and tricks you need when you want to solve numeric. But let's start with the equation itself and how you can strongly solve it. So here's kind of the one equation. Many of you are extremely familiar with it, maybe not with the exact numerical coefficients that we have here, because there are lots of different coefficients going around. And of course, you can just rescale the parameter z and rescale the function u and get this 1/6 somewhere else, or get other numbers like 1/3. But this is a convention that we use in our paper from 2011. That's called the string convention. It's a second order ODE. It has a lot of poles, as you can see in these numerical plots from solutions. So these are contour plots, and all the white plots are poles and several solutions. And of course, because it's a Painlevé equation, these poles can move. They're actually all movable singularities. But only one fixed singularity is infinity, and other than that, it's movable. As you can also see in this picture, there's 3 types of solution. The general solutions have poles throughout the complex plane, but then there are special concave solutions that have part of the complex plane without poles, and then there are very special free-concave solutions, 5 of them, which only have poles in one of these 5 sectors that are marked in red. The fact that there are these 5 sectors is also very well understood. If you play with this equation a little bit, you can see that by multiplying z with a fifth root of unity and multiplying u by another fifth root of unity, you can get the original equation back. And so there's a Z5 symmetry in space of solutions. And that Z5 symmetry shows up in the individual solutions as well. Because the poles tend to line up in the sectors.
What's the significance of that little blue dot?
I'm going to tell you that at the very end. It's the point where we put the boundary conditions of the numerical solution. So actually, I'm going to tell you now. I'm going to connect to that. So that's now solved the solution, but not numerically. That's the formal solution. It's also very well. So if you look at these plots, in particular the ones that have some sort of quite regular behavior at infinity, this of course doesn't mean that the solution is 0, right? It's just smooth, and that's why you can see anything special happening. If in those sectors you go to infinity, you immediately see that the solution you go like square root of that, simply because there's a new square in the equation. If the solution is smooth, then this term is not dominant, and so u squared has to be there, and therefore you can start the square root of that. And then if you try to build a perturbative solution on top of that, you find that there are corrections z to the minus 5/2. And this is an asymptotic series, so it doesn't converge. And that tells you that you might want to look at more general solutions. And there's another thing that tells you that you might want to look at more general solutions, which is the fact that there are no integration constants. This is just one formal solution, but it's a second order ODE, so you expect 2 parameters. And basically what we did in 2011 was to write a full 2-parameter formal solution, formal transseries solution that did contain 2 parameters, sigma 1 and sigma 2. So U00 here is the solution above. And then there are other sectors, maybe by an n and an m, that are corrected by non-determined transmonomics. A little bit of small print. I'm not going to talk about this today, but these U and M in general are not just perturbative expansions, there are also part of the block Z in there. These come from the fact that there's resonance. There are 2 instant-on actions if you want that have opposite sign, and those in the end make sure that these laws of Z are there, but they're not going to be important in this talk. They're very important in understanding them. So in 2011, we constructed the equation. By constructed, I mean we computed a lot of coefficients, the structure, which is the large order behavior of coefficients, and so on. Following this work that I mentioned earlier by carefully this by I think I said Takei instead of so those would follow up. And so we constructed this in a lot of detail. Now, if mathematicians stare at this and they don't know the answer yet, they might be a little bit worried because there's 2, well, physicists like to call it instant action, right? 2 exponents in these transmonomics. There's e to the minus n a z to the 5/4, and there's e to the plus m a z to the 5/4. And so there are really 2 of these instantal actions, the numerical value. And you might say, well, then this is not really an asymptotic expansion of anything. One of these is growing, and the other one is becoming smaller. And this is a question that people are worried about. And for example, Takei gave a talk at the workshop here about how we might want to address this. For today, the story is going to be that this is not really that big of a worry if you're interested in the right questions. So first of all, this is of course fine as a problem. You can just plug this into Painlevé I, you get a good answer. But as we will see today, it's also fine for numerics. So the fact that one of these grows like crazy is not that bad if you use the right tricks to resum this thing and get boundary value. So you can get actual Painlevé I transcendents as long as you don't basically want it. Now, of course, morally speaking, this is still some sort of asymptotic expansion, and so you expect Stokes phenomenon to play a role, and you expect some Stokes phenomenon in particular to act on these parameters. This is very well known if you
for the moment set sigma 2 to 0, then you just send one parameter transseries, which is actually minus asymptotic expansion. And then it's well known that if you cross the real axis, which happens to be the Stokes line, then you can still think of this as an asymptotic expansion, but then you have to shift sigma 1 by a constant. And this constant has been computed, and that's the one that I mentioned before, that's known analytically. I think in mathematics it was originally computed by Takei, and then probably independently by Takei. In physics, François, I think was one of the first to work with this and compute this concept. So that number is not, and that's the number that we originally wanted to generate. And by generalizing, I mean, now we would like to know what happens to both of these parameters if I cross the Stokes lines of sigma 1 and sigma 2 should go, and I actually wrote it wrong here, to a function of sigma 1 and possibly sigma 2, and our function of sigma 1 and sigma 2. And I have to mention resurgence, at least the ones, of course. You can use resurgence techniques as we did in our 2011 papers and particular bridge equations to study large order behavior of certain coefficients. And if you do that, you can read other constant numeric occur in large order behavior, for example, perturbative coefficients, but also coefficients like one sector or two sector. And if you study that large order behavior deep enough, you'll see the Stokes constant appear. So that's how we got those numbers.
Sorry, what is the column that's headed order mean?
Yes, so it's, this is still taken from the old paper. So what we do in the paper is we study, for example, the large order behavior of the 2-0 instant on second. That large order behavior does not depend on this Stokes constant. It depends on another one, but then you subtract the Borel summation of that one from it, you get the not a to the minus g corrections, but 2a to the minus g corrections. Those again depend on another one. Actually subtract the Borel summation of that, and 3a to the minus g corrections. Those depend on the Stokes. So they basically tell you what type of computation you can do that correct constant.
I'm a bit confused about the number of Stokes data there are. Usually there are.
Yeah, but so this is not all. Those are just the ones we managed to compute. There are infinitely many.
Okay, so infinitely many is corresponding to each of the big and that is shown in the fancy.
There's a relation. So every alien derivative tells you something about the different substances. That's not to say that all these numbers are independent. You can check this with the Cardo's collaborators. They're really, in a sense, only two that are independent.
Yeah.
But yeah, as Stokes constant very true. So here are our original questions. Again, the questions from 11 years ago. And of course, when you want to answer these questions about exact values, exact relations, exact Stokes, exact Stokes constant, and numerics is not the way to go. And so there are two ways that are the way to go. Basically, the way that started to work with Ricardo and his collaborators, which is the structure between the Stokes constant, and then in the end find out that there's two that you still need to know. One of them turns out to be the S1 that was well known, and the other one didn't actually complete in the That's one approach, and the other approach that I know is to apply the theory of information. Ricardo is also mentioned, which was also investigated in partly unpublished work by Iwaki. And so what we set out to do is to look at this second approach and really spell it out in detail. So this is where I have to tell you about isomonodromic deformation. And this is where I feel even more scared because there are experts in the audience that know much more about this than I do, but I'll see how well I do, and if you ask questions, then I'll be sure you from my student to answer them if I don't know. But the idea is very nice, and I can tell you what the idea is. Now, many people have worked on this. Like I said, the people in the audience now really has to follow up in this direction. There's quite a large Russian school of people who worked on this. But the formalism and the notation that we use is the one as developed originally by Takei. So that's the language I will use. And one of the things, if I really want to use that language, is that I have to rewrite Painlevé I equation a little bit. So now I'm going to do a thing that's very bad didactically. I'm going to completely change notation and write the Painlevé I equation in this form, just so I connect to the known literature and known foundation. So what I used to call U, the function, the transcendent becomes lambda now. The parameter that I used to Z T. And then you also see that I introduced a new parameter in here. This parameter doesn't really have any mathematical meaning, maybe in the sense that you can always scale it away. Just like you can always scale the 6 to become 1/6. You can also scale this one away. But it's very useful bookkeeping times because it tells you, well, it will turn out to tell you how many powers of certain quantities there are in the answer. So it's a really nice counting parameter. You want to think of it as a large parameter. See, there's also a physical interpretation, as you'll see in a moment. It's basically the inverse of Planck's constant. I didn't write the solution here, but in the solution, of course, we have the integration constant sigma 1 and sigma 2. Those I will now call alpha and beta again for the terminology. So what the idea is now is not to look at this nonlinear second order ODE, but to look at a related linear system of partial differential equations of constant solution Y. Y is a two-component vector, and therefore A and B here are 2x2 matrices. They look rather ugly, but we'll see what they are in a moment. And then you have two two partial differential equations with respect to a new variable x and a variable t that's the variable that we knew before. So here it is again, system of equations and the exact expressions for the matrices A and B. So like I said, x is a new variable, but t we want to think of in the end, and I'll tell you how, as the variable of Painlevé I. In here, though, it's just a parameter that you can use to deform the system. So you see an explicit tree here, I change t, equation change. But you also see a lambda here, and in the end, lambda is going to be some expression in t, some function of t. And you also see a nu in here, which is by definition the derivative of this lambda of t. So this is a whole class really of equations, and I can deform them. Well, I could in principle deform them in two ways, by changing t or by changing lambda as a function of t. But now you might ask, is this even a consistent set of equations? Can I first act with dx and then act with dt, and is that the same as doing it the other way around? You can show that that is only the case if lambda is actually the solution to the Painlevé I equation. So this is how we sort of reformulate Painlevé I. We formulate it as a consistency condition and this linear set of equations. And so a little back of the envelope calculation shows you that lambda has to satisfy Painlevé I. So then you can still deform this this system, which can only deform it by changing t, because lambda as a function of t is already. And this is actually the deformation that we talked about with the isomonodromic deformation. I'll explain the rest of the work there. This was still an equation for two variables, but if you have two linear first order equations, you can of course reduce them to one linear second order equation. If you do that, you find an equation that maybe looks a bit ugly, but to a physicist looks pretty nice. Because it's a Schrödinger equation. You have one second derivative, and then you have a whole bunch of stuff that you can think of. It's potential. And so then you say, okay, I have Schrödinger equation, I have potential, it depends on this eta, so it's h bar dependent, so it's maybe not the most classical example of quantum problem, but still it's a quantum problem. You can try to use, for example, exactly to solve it, and then to learn something about the lambda of t. And that's the approach we're going to take. So now let's talk again about Stokes phenomenon a little bit. That's where I want to go. So we have the Schrödinger equation. Everything that was in this ugly expression I now put into something that's q, except for a prefactor of eta squared. And this is where the relation to h bar comes in, right? This is where you would write h bar and then h bar squared. 1 over h bar. And so, well, the Schrödinger equation being a second order equation has a basis of two solutions. And so we're interested in if I fix this basis by some requirement, for example, that I have one solution that decays and one that increases. And then I start walking around in the X plane. At some point, like the basis transformations and the Stokes phenomenon. And we'll always assume that psi minus is in the game. So more precisely, what happens is that you can call the Stokes diagram, and whenever in this linear problem across one of the Stokes lines, you need the basis transformation, just to make sure that psi minus is still the game. Written out in a bit of detail, these basis transformations take a rather simple form, because you can always take a growing one to not change across such line. And so all you have to do is add enough of the previously growing one to the previously decaying one, so that you get a new decaying solutions. And so they always take this diagonal form with ones on the diagonal, and then either one constant here or one constant there, depending on whether the top one was the decaying one. We're not really interested in going in between, so you could go from segment 3 to segment 3.5, and then to 4. We care about, because at infinity these Stokes lines come together. So the Stokes phenomenon in here, note that at this point this has nothing to do with Stokes phenomenon for NP1 yet. We'll have some Stokes phenomenon here. It's described by basically 5 numbers, and 1 and 2 and 3 and 4 and 5. But you may expect there to be relations between these numbers. If you go around, you have to be careful, because you find a square root range at some point, but if you also include that, then you might expect that if you go around once, you get back to your original solutions. And that gives you some sort of condition on the matrices, and therefore a condition on numbers. And of course, that condition is there whether you start from 1 or from 2, or from 3, 4, or from 5. So actually, these 5 numbers that you find are not really 5 numbers, or they're not 5 independent numbers. Only 2 of them turn out to be independent. So once you fix 2 of them, you know exactly what your solution is doing. And these are called in general monodromy data in the problem. So here the word monodromy comes in again, that's the monodromy. Now I still have to tell you what the ISO then means, and of course what all of this tells us. So now let's go back to the Stokes phenomenon that we're actually interested in. Stokes phenomenon of Painlevé I in this T plane. And it turns out that the shape of this graph that I just showed you, of course, depends on the potential of the WKB problem. And so it depends on the specific solution lambda of T that I plugged into my problem. So if I change T, then this lambda of T will also change, and then the graph here will change. And if I change T just randomly in the T plane, then the topology will stay the same. But you can show that as soon as you cross a Stokes line in the T plane, the topology of this diagram also changes. So here I gave an example where I put T close to this Stokes line, and T on the Stokes line, and then T on the Stokes line, and you see that in the corresponding diagram for the WKB problem, that means that actually these 2 turning points get connected, and then you get disconnected again. So the topology of the Stokes graph, the linear problem, changes when the T plus the Stokes line, the non-linear equation. And this we want to use to our advantage to learn about T. Now, of course, well, it can be shown that the monodromy data and K that we were after, that they only depend on the choice of the K solution, but they do not depend on the value of T. This is something we can do. And this is the ISO and isomonodromic. So ISO means the same. So even though I deform the problem, the monodromy data stay the same, and hence this is called isomonodromic. So even though this picture changes, if I start here with a certain solution and go to there with a certain solution and then go through the picture, the monodromy data should still remain the same. And that's something that we can use for a time. So this brings me to a strategy that we employed in the paper, and that's of course has been known for a few decades already. But that we work out in this detail. So the strategy is to study the interlinear Stokes transition in this picture. We only need to study two of them basically, because we only need two of the Stokes data, the MKs, to be known, and after that all the other ones are. So we look at, for example, starting with 1, going to 2, going to 3. And once you know that, you know how to go to 4. And we want to do that before and after such a topology change to learn something about this. And what we then want to do to answer our questions that we're interested in is express these Stokes data of this problem, M1 and M2, in terms of the Painlevé I solution that we fixed, or more concretely, in terms of the integration constant, alpha and beta. We want to find a map that tell you what M1 and M2 are, when you know what alpha and beta are, or the other way around. And then we know two things. We know this topology of the graph changes if we do a Stokes transition in the linear to the nonlinear problem, but we also know that the Stokes data do not change. And so if we do this before and after the topology change, then alpha and beta must change, because the Painlevé I solution, well, Painlevé I parameter changes. But we know at least that M1 and M2 should stay the same. And so if you do that correctly, you get a connection formula that relates the alpha and beta before the Stokes transition to the alpha beta after that Stokes transition, and that's the result that we were after.
Can I just ask,
Yeah.
in the second dot point, when you say express, what does express mean? Because the mapping between the two sets is transcendental.
Yes, well, yes, but you can write it out. Exactly. I'll show you. You can write it explicitly. I'll show you the expression.
You might have a philosophical difference about what explicit means in this, but please.
Okay, well, let's look at the formulas and then you can tell me whether you consider it an expression or something else. That's fine. And I'm not going through the steps because that's a lot of hard work, and so well, say we did a lot of hard work, but I put on some picture here. Alexander actually did a lot of hard work. And actually found this expression. So this is the type of expression that we find. So if you know alpha and beta, you can actually just compute M1 and M2. The other way around is harder. So if you know M1 and M2, then alpha and beta are not even uniquely determined. So in that sense, an expression is not possible. But this is what I would call an expression M1 and M2 in terms of alpha and beta. So this is before the topology change. This is after the topology change. You see that indeed the expressions are different, but you also know that M1 should remain the same and that M2 should remain the same. So now implicitly you have an expression of the old alpha and beta in terms of the new alpha and beta. And so this is a connection formula. It tells you how to connect the parameters before the Stokes.
So M1, M2, and M2 prime look the same, apart from alpha prime and beta prime.
Exactly, it might be.
Yeah.
Well, and one is not right, and two. It might be that in this case, if you get switch Stokes transition, it might be that for this Stokes transition and two takes the same. Of course, if you look at the topology, that kind of makes sense. Because if you go from 2 to 3 here, nothing really changes. If you go from 1 to 2, the topology really does change. So that's correlated somehow to the fact that one of these formulas stays the same and the other one does. And if you go to the next sector, then
It's like you're trying to that you should between yeah.
Yeah. It's very well.
So there are cases in alpha and beta for which the denominator becomes 0.
Yes. I'll come back to those in more. Those are the interesting ones where alpha beta equals basically not from minus. Those are very interesting. And actually, the whole product alpha beta is an interesting variable anyway that you mentioned that in the slide anyway. So it's very useful in computations to always first think about the product of alpha and beta and then try to compute alpha and beta in the picture. The product of alpha and beta in the WKB language essentially is the leading order of the energy when expanded in each bar. You have to do some variable transformation. Essentially, that's what it is. So now that we have these formulas, we can start computing things and see what happens as things look like. So let's do that. So here I mentioned this product alpha beta. This appears mostly in exponentials, as you can already see in these equations, not only, but here in most form. And in fact, you can show that even though the solution after an Stokes transition can come back to itself, this alpha beta does not need to come back to itself. And you actually have to do 10 Stokes transitions. That's always a bit annoying for Painlevé I, because there's also branch points. So after 5 Stokes and anti-Stokes transitions, you're back to another round, and then you're really back to your original expression. So you need to do 10 Stokes transitions. But this E naught or this alpha beta does not necessarily come back to itself, and it finally shifted by a multiple of an integer, and that's actually because it appears in these exponentials a lot. So there's a 2 pi I n, 2 pi I n then appearing, which cancels. But still, of course, even though this product might not come back to itself, do expect the Painlevé I solution itself to still be the same transcendent that you described. So in this way, you discover some sort of symmetry in the transseries representation. If you shift alpha beta, so you shift E0 by 4n, so you shift alpha beta by 1/2 or n times 1/2, you sort of expect to be describing the same solution. Here you see the same 1/2, by the way, that I just mentioned. That's again not a constant. And so you can show that this actually happens. See what happens if you change alpha and beta. So you start from some value of alpha and beta that you picked, here 1/4, 1/5. You do the transition to compute the new alpha and beta step. You can do analytically. You find some new value and you do this 10 times. And if you're lucky, you get back where you were. And you can start from another one. But the actual picture looks more like this. Where you start here, and then you would expect to go here, but you could also go there 1/2 shift to the left, or there 1/2 shift to the right. And then you can do some sort of case transformation if you want, and transform back here to another Stokes transition. To get here, which might also end up here or there, and then if you want, you can again get back to this fundamental strip in the middle from -1/4 to +1/4. And that's true for pretty much any solution. So it's more like the parameter space, a little bit like a cylinder instead of really. Now I told you about alpha times beta, of course, in individual alpha and beta, the individual integration constants do, and we can compute as well. So for the example of 1/5 and 1/2, we did some Stokes transitions and to other numbers. You'll get again other numbers in the other direction as well. So you can really compute the alpha and beta after one Stokes constant. Note that I just checked here that the product indeed either it stays the same or it never does here, or it changes by 1/2, for example. So here plus 1/2 plus 1/2 minus 1. And again, all of these we expect to be the same monodromy data and the same solution. So the same thing as we want this time. But that's something that we want to check numerically, but we can only do it for the Before going to numerics, though, let me tell you a bit more about special solutions. We also answering earlier question. What about special solutions? Well, the best known special solutions are, of course, the concave solutions, concave solutions. And if you're naive and think about this for the first time, you might say, well, the concave solution probably is just setting alpha and beta equal to 0. And that is true to some extent, but we'll see that it's not the whole truth. And similarly, you might say, well, a concave solution just means either putting alpha to 0 or putting beta to 0. And then a general solution would be no restrictions on alpha and beta. And while all of these statements are true when you read them from right to left, they're not all true when you read them from left to right. And we can realize that now because we have the shift symmetry. Alpha times beta can shift by 1/2. And so if I start from alpha beta 0, 0, then I should also be able to find the treatment K where alpha times beta is plus 1/2 or minus 1. So what is true is when you say this for the actual Stokes statement. The treatment K solution is well known that you get a treatment K solution by sending 2 consecutive Stokes to equal to 0. And some K equals a single one to 0 and a general solution is none of them 0. And so now we can ask what does this mean for these transseries parameters, alpha and beta. Well, a simple example to see why the previous statement was not true. Alpha beta equals 0, 0, indeed is the treatment K solution. But then after you do this Stokes jump, you already get alpha and beta equals to S1 and 0 after shifts by S1. And so it's no longer true that both of them are 0. And as we know, I can just say the product does not need to remain 0. Won't remain 0 in this very simple example, you can go outside this fundamental strip.
Can you please remind me what the fundamental strip was?
By fundamental strip, let me go back to the picture. I mean the solution that is in blue here. Right? So this solution is the same candidate transcendent as this one and as this one. They're very equivalent, so I can always choose one where I'm doing -1/4 and +1/4.
But what does the strip mean in the Stokes lines? Is it some sort of a special initial condition or something?
It's a special choice of parameters for the transseries. You take your, in a sense, you take your parameters for the transseries as small as possible. But for the actual candidate solution, it doesn't mean that. That's the whole idea. It's a symmetry. You could choose another strip. As a side remark, that's actually an interesting remark. It's very interesting to study what happens if I take 2 consecutive of Stokes data and I set them equal to I. You may well know what happens then if you set 2 of them equal to I. Another one is going to be 0, and you're actually talking about the Vonk or the treatment K solution. But what does that mean for alpha and beta? Well, it means that if you go back to our connection formula and you want to compute alpha and beta from the MKs, then at some point you're going to have to solve this equation. So you have this 1 plus the product of the ends here, which happens to be 0. But that should be equal to e to the 4 pi I alpha beta with the sign. So there is no solution. So if you are in this Stokes region and you want to find transseries for these 2 connection for these 2 Stokes data, then actually there's no solution. You have to sort of send one of the multiple to the thing. So we don't have a singular transseries point where you cannot really find a non-equal transseries.
Sorry, one question, but that's not only if both of them are equal to I. I mean, it's the product equal to -1, right?
That's true, but only if both of them are equal to I, you get this equation. So if one of them is 2I and the other is I over 2, then this equation is not complicated in constant. So yes, so yeah, what you really need is one of them to be 0, but you need to start from the sector where. So here an example to show what happens. Say I do start from my favorite treatment K solution with alpha and beta 0. Then of course I have a 0 parameter transseries. You do 1 Stokes transition. I get S1. This is S1 in the convention alpha and beta. And so I get 1 parameter solution with a very particular choice for this 1 parameter. But then if I try to do it again, I'm exactly at this point where I would have to send beta to 0. So I get a single solution, and then do another one, I get a single solution, and then I get back into territory where I can try on transseries. I get 1 parameter or 0 parameter. That way I can go through that. And the same is true for Vonk, that's the number you can get one. And you also see 2 parameters. So the overall picture that is the better way to look at this is that if you want to have a general type, I'll tell you why this is what we have to type anymore. If you want to have a general type solution, you always have 2 parameters that are non-zero. But a Vonk solution can appear with 2 parameters non-zero or 1 parameter non-zero. 3 Vonk can appear with 1 parameter non-zero or both parameters zero. It actually can occur with both parameters non-zero as well, depending if you go outside this fundamental strip. So if you're willing to do that, then you get the two parameters transfer. And from case and triple case, it sometimes can also be the singular transfer. So this is the shortest section of the whole story because, well, like I told you, I have to of course show you that we can also get back this Stokes constant. But that has now become a very simple exercise because once you know this connection formula, well, this connection formula basically are the Stokes formula. Right? We tell you how to go from one side of the Stokes line to the parameter to the other side of the Stokes line. So you can really just expand that equation, compare it to where the Stokes constants appear and read them up. And indeed, you can show that you find these nice numbers that were previously found by parallel and friends. And it should be numerically, of course, they agree with what you found numerically in 2011. So this has now become a rather simple calculation after the project done all the other parts. So let's see if we can numerically see what this is true and not true. So we checked several of these results numerically. And the way we do this is a 5-step program. And now I'm going to be very bad didactically again, because this we then did in the old parameters where what I call lambda of t from O to the fourth now is use that again, alpha and beta are sigma 1 and sigma 2. I have had more time to prepare this program. I think it's nice. I hope you can bear with me. So the program is to do this numerically. You pick some parameters, usually alpha beta, or calling them sigma 1, sigma 2 again. You pick a value in the complex plane of the Painlevé variable, and you compute boundary values from the transseries at this point. I'll tell you more about how to do this at the very end. You compute these boundary values from the transseries. And then you numerically solve the Painlevé I equation. I'll also tell you more about how to do that later. But basically, you just start from this and you integrate the equation numerically. And then from that, you might say, well, now how can I get some data that I can work with? Well, the best data that the Painlevé I solution has is the location of the poles, which can be very easily extracted from this numerical solution. So you just extract where these poles are, and then you have a list of numbers that you can compare to other solutions. So that's the idea that we want to do. So let's do some examples. Well, the simplest example is the Takei solution, and I start with the simplest way of writing the Takei with both parameters equal to 0. And then the most boring thing you can do is a forward Stokes transition across the real axis, because that's you already very well know what the answer is. Gives you that sigma 1 because the Stokes constant is equal to remain 0. And going in the other direction is not much less boring because then sigma 1 stays 0 and sigma 2 essentially gets shifted by a Stokes constant multiplied by I again. But it's a good check on our numerical algorithms, of course, to see if at least these parameters, and these parameters give the same transcendent, because then we can apply more complicated. So here's a picture, and now here comes what the blue dot is important for. The blue dot is the point Z where we compute boundary conditions. So here we did it before the first Stokes transition, here we did it after the first Stokes transition, and here we went backwards and went across this Stokes transition. And you see that indeed you get exactly the same numerical solution. So here sigma 1, sigma 2 are 0, 0. Here they are 0 and S1, and here they are I times S1 and 0. So to the naked eye, this looks very good. It looks the same. You can also try to quantify it as you want the way that I just said. Compute where the poles are. These are the poles, and within the poles, I've written to how many decimal places the poles from one solution match to the poles in the other solution. So this compares the first two pictures. This compares the last two pictures. And I don't know if you can read it. Might be a bit small, but they agree to at least 20 decimal places and 25. So that's a good sign. So then let's be bold and go a little bit further and look at the Takei solution, where sigma 1 is non-zero and sigma 2 is still 0. Then you don't want to do a forward Stokes transition, because that's again just adding S1 to sigma 1, and that will we know and trust away, but you might want to do a backward slope transition. Or both of these parameters now become functions of the old sigma 1. And you see that indeed sigma 2 does not just shift by the Stokes constant, this is almost a Stokes constant. But also there's an imaginary part and this is different from the Stokes constant. So this is really a non-linear map, and it's nice to check out. We could write these numbers and but they would be very interesting. So here's the result, and indeed we went from here now backwards to here, and to make an I solution again looks exactly the same. It's not perfect as treatment okay, of course, but it's all matched to 17 decimal places in this region and 15 decimal places in that region. So that's a first good connection, but connection formula. Maybe a general solution as well. Now we take both parameters non-zero. You see that I take them very small, by the way. I'll tell you why I have to take them small. But you also see that even though I take them small, still a lot of stuff is happening here, right? But these balls are really coming in from infinity to very close to the origin. But these are still very interesting. And now the forward slope transition is interesting, and the backwards one is interesting. I think you take more decimal places because see some changes only at very many decimal places. But the pictures again look very nice. So we do it before the slope transition, after the slope transition, and after the backward slope transition. We have the exact same types of plots and locations of poles, or generally again they match it to 15, sometimes 20 or even more decimal places. In general, the forward slope transition is a little bit better than the backward one. And when we do get that result, that either because the sigma that we took is already a bit too large for numerical purposes, or sometimes just because the numerical solver screws up there's some values in there, and sometimes it's that's, for example, what happens here. Now there would be one more step that we would love to check, but we were not able to. And that is to check this symmetry, this 1/2 symmetry where you change alpha times beta by 1/2. However, this is very difficult, and we were not able to do it, like I said, because when you go outside this fundamental string, it means that you have to pick one of the sigmas or alpha or beta large, right? If alpha times beta larger than 1/4, then at least one of them has to be larger than 1/2. And that makes it very hard to get conversions when you do some transfers. So we tried this a bit and we got some pictures that looked alike, but it was not good enough to actually show or put in the table. So all I can say right now is that this is not possible to check yet. And the problem is really that you would like to keep both of them small, but maybe you would like to keep at least one of them small. Remember what the transseries looked like. The sigma 1 to the n multiplied by t to the minus a n to the 5 there. And we have a times sigma 2 to the n into the plus to the n. And so if you pick some z, then either this one is going to be very big or that one is going to be very big. So you might say, well, why not just that's sigma 2 corresponding to the very small. But then you have the problem that there are also secondary for n and m are both 0, so no mountains appear. And so then you're still in trouble because sigma 1 times sigma 2 is big there. And then try to solve that by actually z accordingly. Make z very large and maybe then it converts. But if z becomes very large, then one of these guys becomes extremely large, this is exponential. And so you have a combination of this really. You just were not able to figure it out. If someone wants to go at it.
Sorry, diagonal sectors of the transcendent. What does that mean?
And equal to m. So basically means that this counts. So still some nice checks, I would say, and like I said, I have some time, like 5 minutes, and we can tell you a little bit about how you actually do this. So
So how do you numerically solve the Painlevé I equation? And I'm telling you this because every time I show these pictures to people, they ask me, how on earth do you get them? But it's actually very well known how to get them, because there was a paper by Fornberg and Weideman in 2011 already, where they gave a nice idea of how to compute these solutions. So I wanted to tell you about that. So what's the idea? Well, let's say that we already have the boundary condition. So someone gives you a u of z and a u prime of z at some point. That is not hard to compute higher derivative. You have the Painlevé equation. The Painlevé equation actually expresses u double prime of z in terms of these things. And so you can compute that, the derivative of the Painlevé equation, and so on. So it's very easy to get a Taylor expansion as that just from the first two points, the first two derivatives. And then you might say, okay, now I do what I always do when I integrate solution. I have a Taylor expansion here, so I go to the nearby point, use the Taylor expansion function here, then new Taylor expansion there, over there, and so on and so on. And this is where things go wrong. And the reason that things go wrong if you do it in that way is that one fault. And so as soon as you start trying to do this Taylor expansion process, very close to the fault, use a lot of precision, and because you have to go to dozens of faults, this breaks down very quickly. And the idea is as simple as units maybe. That's why this chess notation, the double exclamation mark for this. Why not take the Taylor series and turn it into a Padet function? So take the Taylor series at this point, or turn it into a Padet function that tends to C fold, go to a nearby point, and then you can have the same thing. And that turns out to work very well. So the trick is basically just to use Padet functions instead of Taylor. Well, there's one more trick you need to do, because this works well unless you really try to go through a pole or very close to the pole, and then still, even with the Padet function, you get in trouble. So Fornberg and Weideman did the second trick, they say, well, take a starting point, and then don't go to the next lattice point, but just pick randomly another lattice point that you're interested in, and try to go there. But don't do that in a straight line, because you might run through a pole. Take a very small step in the correct direction, and see if the solution stays bounded, if it stays small enough. But also do this in 45 degrees and maybe 22.5 degrees to the left and to the right, and just pick whichever one of these stays smallest in absolute value. Continue for there, try to go straight, but take a little detour if you need to, and keep going until you're close enough to your final lattice point and then continue there. And so you get these crazy paths that the computer sort of chooses, because it constantly picks random new points to go to. You can really see that there are regions that the solution then tries to avoid, like these are the solutions they expect. So combining these two ideas, you get very nice numerical solution. And it goes quite fast. You can even make movies. So here I made a movie with particular boundary conditions, and then I changed sigma 1, for example. From K towards the truncate solution, and you see the section coming in, like slushing to the beach on the thin. You can do it for a truncate rate turn on second parameter. So you can see that there's some sort of interaction between the four, right? You get very close, and the other ones start reacting as well. Show you too many movies, but maybe two more. If you change the base of one of the sigma ones, you see that it falls start rotating along. These are the treatment tables. They just wiggle around a little bit, but the new one, then the phase of the corresponding sigma start rotating. And if you don't like it, this type, of like that.
So how do you make sure that you kind of actually, I guess you just implement this, you said that you implement this with the computer automatically. So
yeah,
search this. How do you make sure that every region, if it's random, you get into every region? Or like when I saw your plot, it seemed like there wasn't too much overlap, so I didn't see a lot of lines crossing there.
No, they don't cross. So you
so
well, they do cross actually, yeah. So that's maybe a coincidence that you don't see them cross. But what you do is you make a long list of all the lattice points, and you randomly pick one, you go there and you remove it from that list. And then, okay, so what we do is then you pick a new lattice point, but you do pick the closest one that you want to do. If I compute here and there, and then I pick this one, then I pick that one, and that's probably the reason that not many lines across is the closest one.
So you start reading at one point, and this is kind of generated from one point.
It's generated from one point, and you go somewhere else, and you go somewhere else again, and you do this until you physically go.
And you kind of, every time that you go somewhere else, you do this by hand, like now I want to go here.
In a random number, right.
Okay, because what's nice about this is like, on one hand, it's not like, it's almost like, the density seems pretty stable across, so there's no holes.
No, there's no holes. So really all the blue dots here are points that I want to arrive at. And whenever I'm close enough to one of those, I try to find this. And so every blue dot is arrived at within a certain distance.
Okay.
So you don't get completely empty.
Okay.
And well, maybe to say what's a very nice thing about this is, of course, that now at all of these points, we already have a Padé approximate. So now if you want to find the poles, it's very easy. You just find the poles of that Padé approximate. Look whenever one is a double pole, which is a nice property of the one. So you get this poles almost. One thing I should then still tell you is how do you get your boundary conditions? Don't mean that we have to solve it together. But this is basically what Gerald told us last week. I can just Padé resum the transseries. And here I come back to this remark that I made in the beginning. Is it not a problem that a to the plus m a to the z by 4 is exponentially growing? Well, it's not a problem. Is that if I first pick z, if I fix the value of z, then a to the plus a z to the 5/4 is just some number. And if I then make sure that my n sigma 2 is small enough, then it's going to be a number smaller than 1 or smaller than n bound than 1. And so the sum over both m and n, and n, still converges if you take sigma 1 and sigma 2 smaller. And this is the reason I needed this 10 to the -4, 10 to the -6. So then you just Padé resum these guys, choose sigma 1, sigma 2 small enough. And then the sum is convergent. You usually need like 5, 6, 7 sectors, which is fortunate because if you didn't beyond that, it's quite difficult. And that's how you get the input for your transseries. Well, maybe one more remark. Okay, if I because there's one reason this is still not quite straightforward, and that's that you want mathematical to them after the Borel and the Padé. Now go back to the thing that you actually want to compute, the UZ. And for that you need the inverse Borel. And that's still numerically the final hurdle sort of you have to take. Because what you want to do if you do a inverse Borel transform, well, you want to do an integral of the form, let's call it the parameter S. Borel plane, e to the minus s, z the same thing, and then here sits the Padé approximation to your Borel transform. And the normal s divided by some other thing in S. And these are polynomials of very high order. We want a lot of coefficients there. So in the Borel plane, that really looks like a whole bunch of poles. They start at the first singularity, for example, then they go over poles, but mimicking the branchments. And so you want to integrate this from 0 to some sort of infinity, not across the axis, of course, for example, slightly above. But if you would do that like this, then you can imagine that because there's so many poles sitting here, this function really starts to vibrate and vibrate very, very loudly. So that's very hard to numerically integrate. You might say, okay, well then I do it like this. But funnily enough, you still get this problem, and I have never been able to figure out if this is a problem with mathematica or really some more deep problem. But whenever you try to cross this line, this integration is giving problems. So that's the final
So I have, in my work, we also used something like, we also have to do this numerically. And the way that I found that it works quite well is we first go, you just deform the contour. You first go straight down,
Yeah.
for example, and then you go.
That certainly works. I've been trying that also. That's one to do like this.
Yeah.
But still, if you then keep increasing the order here, I find that at some point it's still not like I said, error. It still gives you the right answer, but it gives you errors and it gives you precision. Okay, so maybe you figure out another way to solve it. I'd like to hear about it. But the way we solved it in our approach, the problem is really just here, because once you get far enough away, this starts decaying and it's fine.
I found out that sometimes Mathematica says gives this error messages.
Yeah.
Because it wants to compute something extremely high exponential position, but if you say then actually ignore it, then you get quite good.
Yeah, no, it's something like that. So one thing you can do is break it up in small steps, and then do a very small step here. That also works. Then you increase the order, and then you don't know how small the next step is. So what we did was something different, which is actually quite funny. You can also just use the inverse of this idea of Fornberg and Weideman. This is the Takei approximate. But when I'm interested in integrating across a very small region, why not turn it into a Taylor expansion? And that works like magic for some reason. So if you just have a small piece of an integral, you make this into a Taylor expansion, then with the integral, you don't get any error. It works very nicely. So that was sort of our, and that's kind of funny that in one computation we need this trick of turning Taylors here into Takei, and in the other part we need this trick of turning Takei into Taylors. And so in the end, it's very hard. Okay, so time to conclude. So we've seen that if you combine the idea of formal transseries solutions with this approach of isomonodromic transformation, you can obtain these connected formula for both transseries parameters in terms of one solutions. Of course, it reproduces the now known values of the Stokes constant, but you get a lot more. The transseries parameter choices are not unique, but actually it's interesting shift, symmetry. That special solutions have this interesting structure, even with the singular transseries appearing there. So you get a much better grip on the space of alpha and betas. Okay. And at these connection formulas, we were nicely able to check. Of course, there's a lot of open questions. The main one, maybe from what I told today, being can you actually test the shift symmetry numerically. We had found some symmetries on alpha and beta, so I said the space starts to look like a cylinder. But of course, we know that the actual moduli space of one is not a cylinder. It's given by these 5 parameters with 3 equations between them. And so there has to be more, right? There has to be more alphas and betas that are related to other alphas and betas. So it would be nice to get sort of similar algebraic geometry description as an algebraic variety of the moduli space in terms of this alpha and beta. Another question that in particular Alexander is very interested in thinking about a bit now is where you can take these connection formula and relate them to another way people like to describe the asymptotics of which is by elliptic equation, by Weierstrass equation. Exposed. There are a lot of people that have worked on that and thought about it by Takei mentioned a bit about this in Stokes as well. So that's an interesting direction of research that might be interesting to also connect to the 2 parameter transfer and say something about it. And finally, of course, this was just one equation, one, but the idea behind this whole project was also, well, there's lots of projects where we don't know the Stokes constant exactly. It might be interesting also from this perspective to know it. So what else can you apply this to? Well, probably to other Painlevé equations. Painlevé II is applied in the Takei paper as well, which is very much the same. But maybe also discrete Painlevés and other integral systems and so on. So the final question is where.
You have a question from Ulrich. Yeah. When considering how the approximants, one sometimes gets an interesting phenomenon of very close poles and zeros, which are generated when the numerator and denominator polynomials have zeros very close to each other. So I guess the question is whether, so, is anything related to this observing your numerical populations?
The answer, I don't know, I never checked that, so we really only worry about the balls, and then what the P is, we don't really care, because if it has zeros and it's small, we're happy anyway. But it might be that the original function has some special property it calls in zero close to areas. That's something I think about, but I don't know.
I don't know if I should wait till we applaud you.
I'm finished, so.
So, what you mentioned, the geometry of the localized space, I just wanted to check that you know that the monodromy parameters, the monodromy data, satisfy a cubic equation.
Yes, yeah.
And so if you were to substitute your transformations between the Stokes data and those monodromy parameters into that equation, what do you get?
Yeah, that's a good question. I never tried. Maybe I was not try. Basically, these equations are not that nice, so we need to play the kind of functions and stuff like
Also the output and heaters are in the exponent when you have the transformation into n and alpha. So I don't think we get it as clear equation.
It's definitely not
It's
going to be like.
It's not really algebraic,
No.
it'll be gamma functions.
One other thing is, of course, the N1 and N2. I was going to say they're originally not expressed in the same alpha and beta. Afterwards they are, so that might work. You might still worry about in both N1 and N2, am I talking about the same product alpha and beta, or should I put in alpha and beta N1 and alpha and beta plus and one? So there are actually details to think about it. But yeah, this could give you an equation of problem number 3.
What's the more comments, but I don't know. I can ask them afterwards.
So maybe this is a question that maybe not anyone wanted to ask for. I remember, so you were talking about the numerical stability by just using the central Taylor series instead of, and then saying that you have issues because when you're close to poles, you shouldn't do it. I remember at some point 27 years ago when we had this meeting here, that Baldino was talking to Carl Bender, and they were actually saying already that at the moment that you're close to a pole, say the function is bigger than 1, you don't deal with the function itself, you deal with 1 over the function, and which also satisfies a simple differential equation. And again, you can use the Taylor series as well. But in that way, you can just walk wherever you want, and you don't need special paths. You can just walk through them.
Yeah. So that might be a picture. So this also works when you want to integrate it.
Yes.
And you can
I was really talking about just the differential equation.
Yeah,
When you have the initial data and you want to walk through in a particular direction, then whenever you get the function gets too large, consider 1 over and continue with that one.
That I can definitely see happening. Whether you also can integrate some expression in terms of 1 over the function instead of integrating yourself. That's another question. But maybe there maybe it's possible.
So you mentioned the Z5 symmetry in the beginning. Does that play a role in the number of Stokes wedges or the number of Stokes matrices and the isomonodromy?
Yes, very much. So the fact that there's 5 sectors basically comes from this.
How does it follow from the screen?
Okay.
Or like intuitively, sort of morally speaking.
Okay, yeah, I cannot give you mathematical argument. If you look at the original A, for example. One thing is, of course, that by I already you can see that along this line there's going to be a Stokes maybe an anti-Stokes, but asymptotic behavior is changing along this line. Now, if you also know that you can rotate this by 2 pi over 5, then there must be an interesting line here as well. So That's one argument to see that there must be this five.
And that's the same sort of, this five is the same five from the isomonodromy construction you did, the five matrices.
It is, yeah.
That's
Yeah,
the same.
so also there, and the two is also the same too, right? Also there you start with five parameters.
Yeah.
But also it produces the two, which are actually two parameters. Solution.
Thank you.
So just coming back to the case where the gamma function vanishes in the denominator.
Yeah.
I talked to Takei about it because I made a comment in his talk, if you remember, about the symmetric solutions of Fornberg one.
Yeah.
And there are other such symmetric solutions for the other equations. When you look at those, they are rotationally symmetric solutions. So just the fact that the equation has a rotational symmetry doesn't necessarily mean the solution does, but there are special cases for which the solution does have this symmetry. And so if you look at the change of the solution from one sector to the next, it's just a rotation. So it's the same distribution of colors from one sector to the next. So therefore, it doesn't have the same monodromy type, Stokes type transition as these more general solutions that we've been talking about. In other words, the Stokes transition in the linear problem will be different. And for the case where you have the rotationally symmetric solution with the zero at the origin, the corresponding solution of the monodromy problem is given by Hankel functions. And so there's corresponding monodromy data for the Hankel functions, which will be sort of filling the gap of the case where you have the denominator vanishing in these expressions that we have. But I thought that might be interesting. I don't know if it is for anybody else, but it's a kind of a transition in the space of initial data. Which I think is what investigators.
Yeah, so you're saying these could be what we call singular transseries, but
Yes.
some not like
Thank you.
connections.
Yes.
Yeah, but it makes a lot of sense. That would be interesting thing to think about.
Any other questions, comments also from online? We have a few people online, so. And if not, thank Marcel again, thank you. Like I mentioned, we can definitely organize online discussions as well. We now have a nice discussion room.
Very nice.